Hi, my name is Alex Lopez, and this is my lab report for Physics 2211 Lab 3. So this lab was split up into two parts. The first part, the purpose was to estimate the mass of a black hole by finding the net force acting on a star which is orbiting the black hole. The purpose of part two was to determine the initial velocity needed for a ship to fly around the black hole without flying into the black hole or flying into the planet that it was leaving from. And these were both modeled using GlowScript. And to give a brief preview of the results, for the mass of a black hole, I got 1.118 times 10 to the 34 kilograms. And for the initial velocity of the ship, I got -4 times 10 to the 7th meters per second in the x direction and 1.5 times 10 to the 6th meters per second in the y direction. The main physics principles used in this lab are shown by these equations here. So in part one, we use the mass, the initial velocity, and the final velocity of the star to calculate dp dt, which is equal to the net force on the star. And this was set equal to the equation for force due to gravity, and then rearranged to solve for the mass of the black hole. And the force of gravity equation was used again in part two to find the forces that were acting on the planet and the ship. And then those net forces were used in the velocity update formula, which was then used to find the position update, which allowed us to model the motion of the planet and the ship. Here on the left, we see the initial conditions for part one. We have g, the gravitational constant, the mass of the star, which was given to be 2 times 10 to the 30th, and delta t, which is 1 day, or 86,400 seconds. And then on the right, you see we find the initial and final momentums, which is used to find delta p and then dp dt by dividing by time. And then the net force is equal to dp dt, which is then used to find the Fnet parallel and Fnet perpendicular, which were used for the vectors in the model. And then at the bottom, we have the mass of the black hole, which is found using the force of gravity equation rearranged to solve for mass. Here are the results for part one. So you can see the magnitude of Fnet, Fnet parallel, and Fnet perpendicular. And then given all of the masses of the black hole, I found the average of all of them, which is approximately 1.118 times 10 to the 34th kilograms. Here's the code for part two. So on the left, again, we have the initial conditions. So you can see we plugged in the mass of the black hole that was just found in the previous part. And then the mass of the planet and mass of the ship were given to us. And on the right, we use the force of gravity equation to find the force acting between each object in the system. So the net force on the planet is the sum of the force of the ship on the planet and the force of the black hole on the planet. And then the net force on the ship is the sum of the force of the black hole on the ship and the force of the planet on the ship. And then at the bottom, we have the velocity and the position update formulas. So in the velocity formula, we plugged in the respective net forces for both the planet and the ship, and then those velocities were then plugged into the position update formulas. So through trial and error, I found that the best speed was -4 times 10 to the 7th meters per second in the x direction and 1.5 times 10 to the 6th meters per second in the y direction. That allowed the ship to get as close as possible to the black hole without falling in. As you can see by the purple colored line, it got really close to the black hole, and then the force of gravity due to the black hole kind of slingshotted it out of the picture. Alright, so to address some possible sources of error in this lab, in part one, the average black hole mass that I found may not have been exact. There could have been some rounding errors in my calculations. And then in part two, there were many different velocities that gave similar results. I just picked the one that seemed to get the ship closest to the black hole, but there were several different possibilities that all got the ship close to the black hole without it falling in. And then for the what does it mean question, we were asked to discuss the difference between the net force and its components and the rate of change of momentum and its components. And the answer is that they are equivalent. The rate of change of momentum is equal to the net force, and thus the parallel and perpendicular components of each will be equivalent as well. And then for the what if question, we were asked to find the initial velocity that would put the spaceship into orbit of the black hole. I found, again through trial and error, that the x component needed to decrease and the y component needed to increase. So I got the x component to be negative 5 times 10 to the 5th meters per second, and the y component to be 1 times 10 to the 7th meters per second. And that allowed these ships to go into orbit of the black hole.